What's up? Here in this video, 3.4, zeros of polynomial functions. We're going to kind of tie everything up in the last three sections of chapter 3. So first, let's talk about the fundamental theorem of algebra. So what that means is that if a polynomial has degree n, then it's going to have at least one zero in the complex numbers system. So it could be a real zero, could be a imaginary zero. A complex number system, remember, includes all real numbers and imaginary numbers. And more importantly, the linear factorization theorem, which kind of follows from that, is that if a polynomial is of degree n, it has exactly n linear factors. So that means a quadratic function, every single time you could write it out as a product of two factors. Cubic, 3 factors, 10th degree polynomial, 10 factors. Now some of those factors will have real zeros, some of them will be repeated, and some of them will be imaginary. So here's an example of that. So if you look at a, 3x minus 2, that function, it's degree 1, so it has 1 0. This quadratic in b, if you factored it, it would be x minus 5 squared, so it has exactly 2 zeros. But multiplicity of 2. So 1 0 multiplicity of 2, or 1 repeated 0. So x equals 5 is a 0 that comes up twice. So you could factor as x minus 5 times x minus 5. C, that's a cubic, and it has 3 zeros, one being 0, and then one being I root 5, and the other being negative I root 5. Because if you were to factor this, you would pull out an x, then have x squared plus 5, and then you could factor that as x plus I root 5, and then x minus I root 5. Alright, and then D, 4th degree polynomial, which means there are 4 zeros. So that's an important fact to know when you are factoring polynomials. So here's an example kind of using all the different theorems we've learned. So if I gave you f of x equals x cubed plus x plus 1 and ask you to find all the zeros, first you can figure out that from the rational zeros test, all the zeros are going to be in the form, any real zeros will be in the form 1, all the factors of the p, which is 1 and negative 1, divided by all the factors of q, which is the leading coefficient of x cubed, 1 and negative 1. So the possible zeros are 1 and negative 1. Rational zeros. So there could be irrational zeros and also imaginary complex zeros. Now you could test them by plugging them in. And if you plug 1 and negative 1 in, you get neither 1 equals 0. So you know those aren't zeros. So that means this function has no rational zeros. But when you use the intermediate value theorem, if you notice that when you plug in 1, you get a positive number. So you get 1 comma 3 and negative 1 comma negative 1. That means there has to be some 0 on this interval between negative 1 and 1. If you look at a graph, you can see that there's exactly one real 0. And if you understand that this is always increasing this function, then you also know that there's only one real 0. So that means, using the fundamental theorem of algebra, there has to be 2 complex zeros, because there's got to be 3 total, and if one is real, the other 2 have to be complex, because there has to be 3 total. Alright, so find all the zeros of this function. So what you would do is do synthetic division, and just start trying numbers. Like if you tried 1 with synthetic division, so you're looking at all the zeros of 12, so like 1, 2, 3, 4, 6, 12 over all the factors of 10, so like 1, 5, and 10, so plus or minus, so there's a lot of things you could check, but since it's a cubic, once we find our first zero, then we could do the quadratic formula with the rest of them. So if you had no graph, you would just start off with 1 and see if that was a 0, and you would actually try to factor it first, but you can't factor this by grouping. So we would try 1, and then that would give us, that would show us that 1 is not a 0. So then, you could try negative 1 or 2. Alright, well, that would take a lot of time. So on a test or a quiz, this might be on a calc version of a test, and you could look at the graph. Or maybe I just give you a 0. So right now I'm just going to graph this real quick. But let me reiterate, if you didn't have a graph, you would have to just try all these until you found one that worked. And then once you found one that worked, since it was a cubic, just do the quadratic formula. So let me go back to graphing. Alright, so if you look at the graph, you see it does have 3 real zeros. One of them is 2. The other 2 look like fractions. If we put that over, the decimal doesn't really help us too much. But at least if we know if 2 is a 0, we can use synthetic division here and find the others by factoring. So now we know 2 is a 0. Like I said, let's do some synthetic division. Put a 2 here. So if I just tried 2 on my next guess, I would have been good. But without a graph, then it could seem kind of helpless sometimes, just throwing random zeros in the synthetic division algorithm. So let's bring down to -10, and then multiply, and then add, and then multiply, and then add, and then multiply, and we get that 2 is 0. So that means this d of x function factors to x minus 2 times the remaining -10x squared minus 5x plus 6. Alright, so we have a negative leading coefficient. So the first thing I'm going to do is factor out that -1 to make life easier. Because now I want to factor this quadratic, 10x squared plus 5x minus 6. Alright, now to factor this, we're going to do the AC method. So find two numbers that multiply to AC, -60, and add to B, 5. So, let's see. You know what, I don't think this factors, so let's do the quadratic formula. The reason why I know it doesn't, because if you go through every pair of numbers that multiply to -60, none of them add to 5. So we have one 0 of 2, and the other zeros are going to be, we're going to do the quadratic formula. So the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. So all over 2 times 10, all over 20. And then just simplify that. So we get -5 plus or minus the square root of, let's see, that would be 240 plus 25. So that's 265 all over 20. And then we should simplify that. Root 265 can't be simplified because it's 53 times 5. So, I mean, we're good. So we have our 2 zeros. Oops, I don't know what happened, but that disappeared. So those are our 2 zeros, and then 2 is our other one. So there's your 3 zeros. Alright, complex zeros. So they're going to come in conjugate pairs. So if you know that 2i is a 0, then you can assume -2i is a 0. Or if 3 plus root 5i is a 0, then 3 minus root 5i is a 0. They always come in pairs, like Noah's Ark, conjugate pairs. So you might get a question like the one on the bottom, where it says find all the zeros of that polynomial given 1 plus 3i is a 0. So immediately you can assume 1 minus 3i is a 0. So you can't really do synthetic division with complex zeros. What you could do, knowing that both of them are zeros, you can find what the factors are. So you would have x minus 1 minus 3i is one factor, and then x minus 1 plus 3i is another factor, and then we could multiply that out and then do long division with that factor, which would have real coefficients once you multiply this out. So we could do, so let's multiply this out. And again, if we know that this is a 0, then we know that's a factor. And also if we know this given 0 is a 0, we could find the other by doing conjugate pairs. So we find the other factor. Now we're going to multiply that out using the difference of two squares, or the sum and difference formula. So it's going to be x minus 1 squared minus 3i squared. Alright, and that's we got by grouping together these first two terms and then the last term. it's in the form a minus b times a plus b. So when we multiply this out, we get x squared minus 2x plus 1, and then minus 9i squared, which would be like minus negative 9, which is like a plus 9. So now we know x squared minus 2x plus 10 is one quadratic factor. And now we could do long division with that and divide it out of the original polynomial to see what's left over. So we're going to have x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. So now we're going to do long division because this is not a linear factor, it's a quadratic factor. So we're going to put an x squared right there and multiply that all out. So it's x to the fourth minus 3x cubed, oops, that'd be a minus 2x cubed, and then plus 10x squared, and then subtract. So the x to the fourths are going to cancel out, and then negative 3x cubed minus negative 2x cubed is like a negative x cubed because it's a double negative, and then 6x squared minus 10x would be like a minus 4x squared, and then plus 2x minus 60. Alright, now we know that this has to be a negative x, so we're going to multiply that out. So it's negative x cubed plus 2x squared, and then minus 20x, and now subtract everything. So the negative x cubes cancel out, and then we get negative 6x squared, and then this becomes a plus 22x, and then minus 60. Alright, something didn't look right. It was right here. This should be a negative 10x. Sorry about that. I just noticed there was a typo, so I paused it. So then this would be a 12x right here. Now, this will make more sense. We know our last term has to be negative 6, so that we get a negative 6x squared when we multiply that, and then we multiply them by the other terms, we get a positive 12x, and then a negative 60, which when we subtract gives us a remainder of 0. So we have our other factor right there is negative x squared minus x minus 6. So let's just find all the zeros. So we got our first two right here, and then factoring that right there, we get negative, or x minus 3 times x plus 2. So our other two zeros are going to be positive 3 and negative 2. So 1, 2, 3, 4 zeros. So recap what we did. We were given a complex zero. We found the conjugate pair. Multiplied and found the factors given those two zeros. Multiplied it out, got a quadratic, which was right here on the bottom, and then divided that out using long division up here. Found our quadratic factor, factored that, and found the other two zeros. So it was a fourth degree polynomial, so we had 4 zeros just by knowing one of them. Alright, Descartes Rule of signs. So the following two things are just rules to help narrow down what zeros you need to look for if you don't have a graph. So if you're going to look at the polynomial and the number of, so look at the sign changes. So like if I were just to make up an example, x cubed minus x squared minus x plus 1. So from here to here, that would be one sign change because it goes from a positive factor to a negative factor. Then from here to here, it's still one sign change. Then from here to here is the second sign change. This has two sign changes. So the number of positive real zeros is either equal to the number of variations in sign or less than that by an even integer. So that means that this right here has either 2 positive real zeros or 0 positive real zeros. Or it has to be less than that by an even integer. Then if you plug in negative x, so if that's f of x, f of negative x would be negative x cubed minus x squared plus x plus 1. This is going to have, so from negative x cubed to negative x squared, that's no sign changes. And then from here to here, there's one sign change. And then from positive x to positive 1, there's one sign change. So the number of negative real zeros will equal 1 or be less than that by an even integer. So if you subtract 1 by an even integer, subtract 1 by 2, you get negative 1. But there can't be a negative amount of real zeros, which means there has to be exactly one negative real zero. Alright, so that's the key thing, less than that by an even integer. So it has to be, if you have an odd number of sign changes, then there's going to be one of those either positive or negative real zeros, depending on whether you're looking at f of x or f of negative x. So let's do another example. So same thing. So let's look at g of x. So the number of sign changes in g of x. So we have one right there, and then we got a second one right there, and then a third one right there. So the number of positive real zeros. So we're going to make a little chart. Positive real zeros and then negative real zeros. So there could be either 3 positive real zeros or 1 positive real zeros. It has to be one or the other because it has to be less than 3 by an even integer. So if you subtract 2 from 3, you get 1, and then if you subtract 4 from 3, you get a negative. It can't be 2 or 0 because that's an odd integer subtracted from 3. Right, so it can't be 2 because that's 3 minus 1, 1's odd, and it can't be 0 because 3 minus 3 is 0, but 3 is odd. Alright, so now let's look at g of negative x. So that gives us negative 3x cubed minus 5x squared minus 6x minus 4. So that's no sign changes. All the odd degree terms will change signs when you plug in negative x, and the even ones will not. So that's 0 sign changes. So there cannot be any negative real zeros. So if we look at complex zeros, well, there's got to be a total of 3. So if there's 3 positive real zeros and no negative real zeros, there's going to be 0 complex zeros. But if there's 1 positive real zeros, which is possible, but no negative real zeros, then there could also be 2 complex real zeros. So here are the possible variations of zeros right here. It could be 1 positive, no negative, and 0 complex. Or if there's only 1 positive, there could be 2 complex. Alright, last but not least, the upper and lower bound rules. So let's say you do synthetic division and you test a 0 that's positive. So c is greater than 0. And each number in the bottom row is non-negative. So you test synthetic division with a positive 0, and the bottom row is all positive or 0. That means c is an upper bound for the real zeros, meaning there are no zeros greater than c. So if you tried 2 with synthetic division and you didn't get it to be a 0, but the bottom row of numbers in synthetic division were all non-negative, then there cannot be a 0 greater than 2 because 2 is an upper bound. And if you test a negative number and the bottom row of numbers are alternating from non-negative to non-positive, then c is a lower bound. So if it alternates positive, negative, and 0 can count for both, then c is a lower bound. So if you try negative 3 and you get alternating non-negative to non-positive in the bottom row, that means there can't be a 0 less than negative 3. So don't test zeros less than negative 3. Test ones greater than. So let's try it. Alright, so find the real zeros of 6x cubed minus 4x squared plus 3x minus 2. So let's divide by x minus 1 and then see what Descartes' Rule of Signs tells us. So let's try 1. When we try 1, we're going to put a 6, negative 4, 3, and negative 2 right there. So if we bring down the 6, we multiply and get 6, and then add, we get 2, and then multiply, we get 2, and then add, we get 5, and then multiply, and we get 5, add, we get 3. So this entire bottom row is all positive, so they're all non-negative, which means 1 is an upper bound. So that means, well, of all the possible zeros, we have could be 1 or 2 over 1, 2, 3, and 6, plus or minus. 1, there can't be a 0 higher than 1, so that means you don't even need to test 2, because 1's an upper bound. So you can eliminate trying 2 over 1, but 2/3 and it might still work. Now, let's look at what a lower bound would, well, let's just talk about what a lower bound would look like. Let's say, hypothetically, this number came out to be negative, and this number came out to be negative. Then that means 1's a lower bound, so then none of the zeros less than 1 would work. So like -1, -2, 1/2, 1/3, none of them would possibly work. Alright? Just a friendly reminder, when you're doing synthetic division or applying zero tests, always try to factor out a common monomial first. So look at the polynomial. If there's a common factor, pull it out first. And if that just makes all the numbers a little less and makes your life a little easier. And if you ever get down to a quadratic, try to factor it first or use the quadratic formula. Never do synthetic or long division with the quadratic because you're just wasting your time. Alright, so let's factor this using all the stuff we learned. Alright, so let's say we had to factor this and we weren't given any zeros, whether they're complex or real or rational or irrational. So we have to test numbers randomly. So all the possible zeros would be all the factors of p, which is all the factors of 8. So that would be 1, 2, 4, and 8. Plus or minus, so it could also be -1, -2, -4, -8, and divided by all the factors of the leading coefficient, which is 1. So then we would try 1, we tried 2, we tried 4, until we found 3 that worked, and then we could just factor using AC method or do the quadratic formula. Just to illustrate something, I just want to try to factor, I'm just going to try -2 first. You should never do that. You should always try 1 first, and then -1, and then 2, and then -2. Start with the numbers closest to 0 first, and use integers first. Because if there's fractions, there's no need to try them. You'd probably find the integer zeros first. But just to illustrate something, I want to try -2 first. So I'm going to try -2, and the numbers across the top will be 1, 0, because there's no x to the 4th term, and then 1, and then 2, and then -12, and then 8. So I'm going to bring down the 1, and then multiply, and I get -2, and then add, and I get -2. Multiply, I get 4, add, I get 5. Multiply, I get -10, add, I get -8. Multiply, I get 16, add, I get 4. Multiply, and I get -8, and there's a 0. Alright, now why did I try -2 first? To illustrate the upper and lower bound rules. So first, this one was non-negative, and then the bottom row, this one was negative. And then the next number was non-negative, and then this one was non-positive. Non-negative, non-positive. So it pretty much alternated from positive to negative with the exception of 0 as the last term, which means -2 is a lower bound, which means we don't have to try -4 and -8. So now we know that -2 is a 0. And now we're going to try these numbers. 1, -2, 5, -8, 4, and 0. So now it's -2 could work again, but let's just try 1 because 1's easier to work with. So now I'm going to bring down a 1, multiply, add, multiply, add, multiply. Something went wrong here. Right here I put a 2. It should have been a 1. So 1 times 1 is 1, and then add, and we get -1. And then multiply, and we get -1, add, we get 4, multiply, we get 4, add, we get -4, multiply, we get -4, and we get a 0. So 1 works too. So right now, we factored out a x plus 2 and x minus 1, because we knew -1, -2, and 1 were zeros, and we were left with these numbers right here, which would represent x cubed minus x squared plus 4x minus 4. Now, we can keep doing synthetic division, or you can notice that this right here can be factored by grouping. You could pull out an x squared here, and you're left with x minus 1. and also pull out a 4, and you're left with x minus 1. And then you'd have x minus 1 times x squared plus 4 times x plus 2 times x minus 1. And if it said factor completely using linear factorization, then this right here, we could factor this last term. So first let's rewrite these so we have room. And then this last term, we can rewrite it as x plus 2i times x minus 2i. Because x squared plus 4, if you set that equal to 0, it'd have no real zeros. If you set equal to 0 and solved, you would get that your real zeros would be 2i, negative 2i, so we could write them as factors. And there you go. That's the linear factorization of f of x. So we use synthetic division, we use upper and lower bound rules, and we factored when we saw fit. Alright, and that is the end of this video. Hope you found it helpful. Have a nice day.